Video number 4, we're going to talk about some similarity in right triangles. There's some crazy stuff that happens here, and this will be the main section. Out of the 4 sections we're doing this chapter, this is the main one where everything's going to happen. So you can kind of think of a papa, mama, and a baby right triangle. There are some similarities between them that we will discover here. So first off, a vocab term, altitude. Altitude is really just a fancy way of saying it's the height of the triangle. If you think back in the day when we would calculate the area of a triangle, which was 1/2 base times height, if we had our base, let's say right here, the height we always said had to be perpendicular to the base. So the height could be inside the triangle, it could be actually one of the sides of a triangle, or it could be hanging out on the outside if it was in an obtuse triangle, where this would be our base and the perpendicular part would be hanging on the outside. Okay. Now the more appropriate term we should call the altitude, besides just the height, it's the perpendicular segment from a vertex, aka from an angle, to the line containing the opposite side, aka the base. Okay. So you can kind of think of vertex as an angle, and the opposite side, you can kind of think of that like the base. Okay, so it's essentially the height of a triangle, if you will, is the altitude. Now, there are multiple altitudes in any triangle. Since it says it's the perpendicular segment from a vertex, well, technically there are 3 vertices in every triangle. So there are 3 altitudes. I just showed you 1 in each of these kinds. So for example, I could draw in, say, another altitude right here from this vertex to this opposite side, and it's perpendicular. I could do the same thing from this vertex going to its opposite side. Let's see if I can make this look good. Yeah, that's not bad. And it's perpendicular. So for any triangle, there are 3 altitudes. Just keep that in mind. Altitude just isn't 1 here. It's 3 possible ways. Now, next question I ask is, what's true about these triangles and why? First glance, you're sitting here going, Mr. G, you said triangles plural. There's only 1 triangle here. Really? Say that again. What I did was I drew in, aka, the altitude here, okay? So if I were to put this on top, you'll notice that these 2 triangles together is the exact same area that they would be congruent to this large triangle. Okay, we call this triangle 1, 2, 3. So these 2 triangles, 4, 5, 6, and 7, 8, 9, together again is congruent to triangle 1, 2, 3. They're the same exact size. So what I drew in here, basically in 1, 2, 3, you know, if you think about from here, and I drew a line going this way and made it perpendicular, was I drew in the altitude from vertex 2 to the hypotenuse of 1, 3 here. So here's what we're going to look at. What's true about these 3 triangles now? Now, if you notice, all 3 of them have right angles. Okay, so if we were looking for shortcuts, similarity shortcuts, we had angle, angle, we had side, angle, side, and we have side, side, side. And right now we know that all 3 of these triangles have 1 set of matching angles. They all have 90s. Sweet. We need something more, right? Well, let's say I just put 1 congruent marking on angle 1. Okay, and let's say I put 2. I'm going to assume 1 and 3 are unequal angles. So let's say I put those markings on there. Well, now let's say I go back over here to triangle 4, 5, 6. And I know that 6 and 2 match up because they're both 90, but let me take this and, just to show you, remember that 1 and 4 originally coincided. So they're at the same angle, right? So 4 deserves 1 marking. So these 2 triangles have 1, 2 pair of congruent angles, therefore they are similar. So we can use angle-angle similarity in the end. And these other 2 shortcuts, not applicable. Now that means, how many markings can I put on angle 5? Because remember, if 2 sets of angles are the same and between 2 triangles, the 3rd set of angles, angle 3 and angle 5, must be the same. So technically I could put 2 marks on angle 5. And so now let's go back to triangle 7, 8, 9. Well, we know 8 and 2 match up because they're 90s, And again, if I put 7, 8, 9 back where it originally was, on top of 1, 2, 3, we can see that angles 3 and 9 were really the same. And if 3 has 2 markings, I can put 2 markings on 9. And with these two triangles, we have angle, angle, which means angle 7 must be the same as angle 1, and it deserves 1 angle marking. Put 1 thick marking on there. So really, all three of these triangles, all three triangles are similar by angle-angle similarity. Okay, so if you draw in an altitude of a triangle, remember if we drew in the altitude here, boom, 90 degrees, that really the original big triangle and the two smaller triangles inside of it are all similar to each other. Now, besides all the angles matching up and being congruent, what does that mean is true about all of our side lengths between these three triangles? It means that they're not congruent, remember, but they are proportional. That's where we are going to start our investigative task. So, first thing we want to do is let's write a similarity statement. Okay, triangle ABC, which is our big guy here, and notice CD is our altitude because it's coming from one angle over to the opposite side and it's perpendicular. And if I really wanted to, I could drop in another 90-degree angle over here because of the straight angle postulate. We have 99 equals 180. All right, so now ABC, we'll call this the big triangle. And let's call this the left triangle, this guy over here, ACD. And we'll set this up for the right triangle, this guy over here, CBD. But we need to get our angles in the right order for our similarity statement. Now, angle C in the big triangle, that was our 90-degree angle, which means the last letters in our other two statements here both need to be the 90s. Well, in the left triangle, in ACD, D is the 90-degree angle. So we know that's got to be a D. And in this triangle, hey, this D is also the 90-degree angle. So we've gotten the 90-degree taken care of. But now, how do the others go? Here's where we want to do what we did earlier. Let me go back to the big triangle, ABC. And let me put one congruent mark on A and two congruent marks on B. Because I'm just going to assume that A and B are different in triangle ABC. Again, we're looking at the whole big thing here. Now, we already discussed that all of these triangles are similar. So now, if A in the big triangle has the one mark on it, well, now let's look at the left triangle, this guy. Which angle has the one mark on it? Well, A does. So A must go in the same spot as that A. Now, over here, we need to look for the angle that has one mark on it. Well, we have the 90, and this has two marks. So that means the third and final angle must get one marking, which is angle C. Okay, so we can put one arc mark up here, and that goes in the first spot. So angle A in the big triangle, angle A in the left triangle, and angle C in this right side triangle all use the same marking. And so now, kind of by a process of elimination, we know what the middle two letters need to be, right? Because if we're looking at this triangle, ACD, well, the only thing we've left out is C at this point. But let me backtrack just a little here. If we're talking about angle B in the big triangle, it had the two marks on it. So which angle in this triangle has two markings on it? Well, none of the angles have two markings, but if this has one and this is the 90, that means angle C here must get the two markings. And in this triangle on the right side, angle B had the two markings, so B goes in the middle. So here's our similarity statement. Big triangle ABC is similar to smaller triangle ACD is similar to smaller triangle CBD. Okay, this is setting us up for what we're getting ready to do next here. Okay, so again, all three of these triangles, the two smaller ones and the big one, all similar to each other. Now, before we can advance on, we need to give our sides some names here. Now, number one, we called this piece the altitude, right? It went from a vertex to an opposite side and made a 90-degree angle. That was the altitude. Now, considering this whole thing is one big right triangle, this piece right here would be the side opposite the 90-degree angle in a right triangle, aka that's the hypotenuse. Now, what did we call the other two non-hypotenuse sides of a right triangle? Well, they were legs. Okay, and in an isosceles triangle, the legs are congruent. In a non-isosceles right triangle, the legs are not congruent. Okay, now we will need to differentiate between this leg and that leg, so I'm just going to call this one leg 1, and I'm going to use a little subscript here, and leg 2. Okay, so the 1 and 2 don't mean anything mathematically, they're just like naming it. Leg 1 and leg 2. Now you might think, all right, we're done, we've got everything labeled. But there's two more pieces that technically need labeled. We need to label AD and DB, okay, the two smaller pieces that make up the whole hypotenuse. We're going to refer to these as segments, or what I will call seg and seg. And again, I need to identify which segment is which here. So if I call this side leg 1, this will be segment 1. So this leg and this segment will use the same subscript. So if I use 1 here, I'm going to use 1 there. Likewise, over here, if I'm calling this leg 2, this is going to be segment 2, the one that's right around the corner or adjacent to that leg. So now I have legs, hypotenuse, altitude, and 2 segments. I've got 6 things I'm going to have to keep straight in my mind now. Now let's connect together the names of all these pieces with our similar triangles. And what we're going to try to do, here's our goal, is to find proportions with matching sides. Okay? And at first you might be going, what do you mean by matching sides? Well, we can only look at 2 triangles at a time. So notice I've got this triangle basically not blacked out completely, but we're going to ignore this triangle for now. We're going to focus on, right, the big triangle ABC and the smaller left triangle ACD. And the first thing I just want to look for here is what side is in both ABC and ACD. And all you really have to do to figure that out is, well, what 2 letters are the same? Well, there's an AC in here, and there's an AC in here. But notice they're not corresponding sides. A and C is the first and last letter of this triangle, but it's not the first and last letter of this triangle. Okay, so here's what we're going to do. AC, we're going to talk about big AC. Well, big AC would match up with small AD, right? Because this is the first and third letters. If I think about this as in a 1, 2, 3 order here, AC in the big triangle is the 1 with 3, and AD would be 1 with 3. So they get to go in the same ratio with each other. So I'm going to set that equal to, and then I need another ratio, where again, whatever I name over here has got to be from the big triangle, and whatever I name in the bottom has got to be from the small triangle, so I match up big with big on top, small with small on bottom. Now again, I wanted to use AC. Now AC, the other AC is in the small triangle, so I'd have to write that in the bottom. Well, AC is the 1, 2 combination here, so in the big triangle, the 1, 2 combination is AB. Okay, so AC over AD is proportional to AB over AC in both of those triangles. Now what we're going to do is replace all 4 of these things, AB, AC, and AD, with their names up here. Okay, so AC, here's AC. That was leg 1. So I'm going to replace, how can I do this here? How can I do this here? How can I do this here? Let's do this. Take a picture. Paste it in there. So I'm going to use this as my reference guide now. So AC, I'm going to say, all right, this AC, it really has the name of leg 1. And AD on bottom, well, AD is segment 1. Okay, so let's get rid of AD. It was segment 1. And hey, here's AC again, and that's still leg 1. So let's erase that. There's leg 1. And AB, well, AB is the whole hypotenuse here. Hypotenuse. All right, so now you might ask, well, what are we going to do with this? Good question. The book kind of leaves it in this format. What I do, just to make a nice little formula, is if I had, a ratio equal a ratio, a lot of times I would want to cross multiply this. So if I were to cross multiply, I'd have leg 1 times leg 1, which means I'm going to have leg 1 squared. Leg 1 times itself is shorthand for leg squared. And that's going to be equal to segment 1 times the whole hypotenuse. This is one formula, one of two, that we're going to be discovering here. So here's one of them. And we're going to see something very similar to this very, very soon. So keep this one in the back of your mind. Leg 1 squared is equal to segment 1 times the hypotenuse. Remember, leg 1 and segment 1 are just right around the corner from each other. They're adjacent to each other. Now we're going to do the same thing, but I'm going to ignore this time this triangle. And we're going to focus on ABC, the big triangle, and CBD, the other smaller triangle. And again, I want to try to find matching sides. So what two letters are the same in both of these triangles? Well, that would be BC and BC. But again, notice they're not in the same positions in terms of a 1, 2, 3 position. So we're going to set up again another ratio, and we'll do big to small, and big to small. So if I want to talk about BC in the big triangle, right? BC, that's the second and third letters. Well, the second and third letters over here, though, are BD. Okay, so now if I want to talk about BC, because that was the thing I wanted to find, was that matching side, which is BC. BC, I'm going to pop down here with the small triangle. It's the first two letters, and in the big triangle, the first two letters would be AB. So again, I want to do the same thing. I want to replace AB, BC, BD with what they really mean up here in terms of their names. So let's see. BC is leg 2. So this really turns into leg 2. And over here I had BC, right? So I got them in both spots. So those are both leg 2s. Then BD, let's see, BD, that's segment 2. And AB, well, that's the whole hypotenuse. So again, if I were to take this now and cross multiply, let's get some space in here. Oh well. If I were to cross multiply this, I would get leg 2 times itself, which means leg 2 squared, equals segment 2 times hypotenuse. Well, that looks an awful lot like the last one we did, right? Because it was leg squared times or equals segment times hypotenuse. This is the same thing, except the only difference is the subscripts, right? This was 1 with 1, and this is 2 with 2. So here's the great thing. You don't have to memorize this formula and this formula because they're essentially the same thing. This formula, though, will work two different ways. It depends on which leg we want to use. If we want to use leg 1, we have to match it up with segment 1. If we want to use leg 2, we have to match it up with segment 2. So the subscripts here, the 1s and the 2s, always have to match together. They will never be mixed together. You won't use leg 2 with segment 1. That'll never work because they're not corresponding sides or proportional sides of our similar triangles. Now, the last scenario is when we ignore the big triangle and we focus on the two smaller triangles. So now again, let's find our matching side here. So what two letters are the same? Oh, what? C and D. And again, notice they're not in the same positions. That's fine. So let's call this guy the left triangle and this guy the right triangle. So as I'm setting up my proportions, we'll have left over right, and we'll have another left over right. And my matching side, again, remember CD, so I'll start with CD in the left triangle. Well, CD in the left triangle is the second, third letters, and it's going to match up with BD in the right triangle. So those are in the same ratio. And now if I want to talk about, again, CD, but CD in the right triangle, it was the first and last letters, and the first and last letters over here are A and D. So once again, let's convert all of this to what their names are up here. And we're not going to get the same thing as we did the last two times. So CD, remember CD was written twice here. CD is the altitude. So this is altitude over something equals something over altitude. BD, let's see, BD, that's segment 2. And AD, that's segment 1. So now if we were to cross multiply, we would end up with altitude times itself, or altitude squared, equals segment 1, and I'm just going to kind of flip the order here. Instead of segment 2 times segment 1, I'm just going to say segment 1 times segment 2. And there's our other formula that we're going to be using quite a bit. Okay, so the altitude squared, so we're focusing on this piece, is equal to segment 1, which is this piece, times segment 2, that piece. So this formula does not use the legs at all. And notice that our leg formulas didn't use the altitude at all, which is a very important thing to note there. So our important formulas, and there's only 2 again, one of them can be used 2 ways, our leg formula. But our first one, or the last one we just discovered, if you will, was the altitude squared is equal to the first segment times the second segment, or we could say the second segment times the first segment. Again, multiplication doesn't matter which order you multiply in. And the leg formula, which can be used twice, notice I'm not using subscripts anymore. So I'm just going to say the leg in general squared is equal to the, now instead of calling it just segment, I will refer to it as the adjacent hypotenuse segment, which will really just be the segment that's adjacent to that specific leg. So if I want to talk about this leg, I'm really talking about this segment that's right around the corner. And if I'm talking about this leg over here, I'm talking about this segment, the one that's right around the corner. So again, depending on which leg we're using, there's 2 different variations of this particular formula. So it was leg squared equals its segment, its adjacent segment, if you will. If you don't want to include hypotenuse, that's fine. We could just say the adjacent segment times the whole hypotenuse. Okay, and the whole hypotenuse was really segment 1 plus segment 2, if you want to think of it that way. Now, this video focuses on no calculations, but just getting these 2 formulas. One last thing. Are there any other formulas besides these 2? Yes, there are other formulas, but they don't have anything matching in them. These formulas get a lot of attention because they had matching pieces. We had altitudes used twice, and we had legs used twice, and therefore we get these kind of special formulas, if you will. Now, I could always run back here, for instance, and just pick, I don't know, let's say AC with this CB. So AC in the left triangle, that's leg 1, and CB is leg 2. And I don't know, let's say CD, the second and the third with this second and third. So CD in this side is leg 1. Wait, no, is that right? ACD. No, altitude. Sorry, I don't know what I'm thinking. CD in this triangle is the altitude. And BD in this triangle is segment 2. Notice there was no direct match here. I mean, I can cross multiply this, and I can create another formula, but it's not considered one of the special ones. So I could say, oh, well, leg 1 times the other segment is equal to leg 2 times its altitude. You can remember that one if you want, but really the 2 formulas that we have, our altitude and our leg formulas, this will take care of it. I mean, our 2 formulas will result in not needing to know any other formulas, okay? But you could make up other formulas that really have no matches, right? Like this has 4 different things being used instead of just 3, right? 1, 2, 3, 1, 2, 3. So there's really nothing special about these 2 formulas other than the fact that they use repeated pieces between your 2 triangles. And that's the connector really to bring together your 2 triangles. So that's all for this video. In class, we will discuss how do we actually now use these formulas to do some calculations. So that's all.